In this video, we will be getting ready for our week 9 labs here in Chem 106 lab. In particular, we will be talking about lab number V10, that is the acid-base lab, or excuse me, the pH and acid dissolution lab, and lab E22, the thermodynamics for the dissociation of acetic acid and the chloroacetic acids. So in order to understand, because both of these labs focus on a couple of concepts, pH, weak acid and weak base equilibrium, and in particular weak acid equilibrium, and a little bit in there about thermodynamics and titrations. And we'll get to that when we talk about E22 specifically. But before we get into talking about each of the labs individually, let's go ahead and look at just kind of the broad concept that we are talking about. And so the broad concept that we are talking about here is the pH scale. Now go back to Gen Chem 1, Chem 105, and you'll recall from Gen Chem 1 that pH is tied to the concentration of the H plus ion, in that the pH of a solution is equal to the negative log of the concentration of the H plus ion in that solution. You probably also remember from Chem 105 that the pH for a neutral solution is 7. pHs for acidic solutions are less than 7. pHs for basic solutions are greater than 7. And that we can find the analog to pH, the POH, by taking the negative log of the concentration of the hydroxide ion. And if I put those two together, pH and POH, they would equal out to 14. These were things that were covered in kind of big, broad brush strokes in Chem 105. And certainly were covered in times before you got to Chem 105 as well. You probably saw a good bit of this in high school. What we really didn't get into too much at the time was where that pH value came from. And it comes from something called autoimmunization. Autoionization for water takes advantage of the fact that water is amphiprotic, meaning that it can act as an acid or as base. And what happens is that water will react with itself to form hydronium ion, H+, and hydroxide ion, OH-. Based on this autoionization, we can conclude that there will always be some amount of H+ and some amount of hydroxide in all solutions at all times. And if we are in a neutral solution, then the two concentrations are going to be equal to each other. But now that we have a better understanding of equilibrium, because we've gone through the equilibrium chapter, we understand that this particular reaction has a constant associated with it. That constant, the equilibrium constant for the autoionization, would be equal to the concentration of the hydronium ion multiplied by the concentration of the hydroxide ion. Now, because this value is quite important, and because the values here are somewhat fixed, especially if we are dealing with pure pH 7 water, instead of calling this and referring to this as Kc like we would any other equilibrium constant, it's going to get its own special subscript. That special subscript is W for water. So the equilibrium constant for water autoionization is equal to 1 times 10 to the negative 14th. That is what I get when I multiply the hydronium concentration by the hydroxide concentration for any aqueous solution at normal temperature. And so from that standpoint, if it is a neutral solution, and taking the square root here, I get 1 times 10 to the negative 7th. The concentration of hydronium in neutral solution is 1 times 10 to the negative 7th molar. The concentration of hydroxide is 1 times 10 to the negative 7th molar as well, which means that the pH of a neutral solution, negative log of 1 times 10 to the negative 7th, gives me 7. So the pH is 7 and the POH is 7 as well. Now, when we have strong acids or strong bases, what we will see is that the concentrations of hydronium for strong acids are so large that they largely dwarf the concentrations of the hydroxides. And so what we get there is an equilibrium value that is very heavily skewed toward the products, so much so that basically we can conclude that the concentration of the strong acid is also the concentration of the hydronium ion. And therefore, finding the pH for a strong acid is relatively easy. All I need to do is take the logarithm of that concentration. For strong bases, similar kind of idea. Since strong bases have considerably large Kb values, we can largely assume that the concentration of the strong base and the concentration of the hydroxide ion are largely the same thing. Obviously, if we're dealing with diprotic or dihydroxo bases or acids, those numbers are going to change slightly. But that's kind of the overall assumption we can run with. And so with the hydroxide concentration, we can find POH, and we can then turn that to pH. If we are not in a neutral solution, we know that we have a counterbalance going on. So the hydroxide concentration and the hydronium concentration are tied to each other. If the hydronium concentration starts to dip up and the hydroxide's concentration dips down accordingly, we're going to see a heavier concentration of hydronium, a lower concentration of hydroxide, and a pH less than 7 as a result. If we get into more basic solutions, the balance starts to tip the other way. We have higher hydroxide concentrations and lower hydronium concentrations. Then we're going to see that the pH trends upward above 7. But notice that in all of the cases, our value for our Kw does not change in any of them, whether they are acidic, basic, or neutral. That's an important thing to remember. So when it comes to acid equilibrium follows this general kind of trend where I've got the concentration of, or excuse me, I've got the weak acid HA reacting with water. The HA acts as a Bronsted acid, gives its hydrogen to the water to become hydronium, and we have the conjugate base A minus here left over. Following our normal rules of equilibrium, recognizing that that water is a liquid and that its concentration is going to be relatively constant, Ka in this case, because A is for acid and we're talking about the acid dissociation here, would be equal to the hydronium concentration multiplied by the concentration of A minus divided by the concentration of the weak acid HA. Ka is also known as the acid dissociation constant because that is the kind of equilibrium that it is describing. Now, the values of Ka vary widely by substance. Your appendices, so Appendix A or Appendix 5 and Table A5.1, there's a lot of your common Ka values there. Those of you that have the lecture packet, the one with all the constants in it, that lecture packet also carries these values on pages 21 to 23. If you do not have that lecture packet, I did stash that appendix table in with your equilibrium skill builder from last week. So you should have a copy of it there in lab archives as well. When we use Ka values, we can use Ka to figure out pH values for weak acids, even though we know that the full concentration of the weak acid does not completely translate to HA. Because it is an equilibrium and because there is a constant associated with it, we can use a Rice table or an ICE table, depending upon your preferred terminology, to figure out what the concentration of the hydronium ion is at that equilibrium state. And if we know the hydronium concentration, then we can certainly figure out the pH. Now, one measure of dissociation is something called percent ionization. Percent ionization is just simply a ratio that looks at how much acid was produced in terms of acidic protons versus how much acid in terms of weak acid was put into the solution in the first place. And so that ratio of H plus essentially divided by HA, initial HA, gives us the idea of how much did we actually see break apart. And that is an indicator of acid strength as well. So with this in mind, and because you're going to see problems like this in the pre-lab for both labs, let's take a look at a problem like this. So what is the Ka for a 0.85 molar solution of phenylacetic acid if the solution has a pH of 2.68? We also need to determine the percent ionization. So the reaction itself that we're looking at is phenylacetic acid, which if you don't know, one of the real nice things about weak acid equilibrium and weak base equilibrium for that matter is that we have the ability to kind of fudge things a little bit in terms of if we don't know the exact formula for something, we know that the generic formula for a weak acid is hydrogen and some sort of conjugate base. So the phenylacetate, we're just going to abbreviate as phen. So phenylacetic acid is H-phen. It is aqueous. It reacts with water to make H3O plus. That is aqueous. And the phenylacetate ion minus, which is aqueous also. So we are going to have to set up our ICE table, or again, RICE table, depending upon what version your instructor and lecturer is referring. But the idea is that we've got a reaction, we've got our initial concentrations, our changes, and our equilibrium state. Well, from an initial concentration standpoint, we know that our phenylacetic acid is 0.085 molar. We know that our hydronium concentration, initially speaking, is 0. Yes, technically we can say that it's 1 times 10 to the negative 7th molar. However, that concentration is sizably small compared to what we're going to get from this acid. So we're just going to ignore that little tidbit there. Same thing for the phenylacetate. Since right now, everything is on the reactant side and none of it is on the product side, we know that we are going to lose some amount of reactant and we are going to gain equivalent amounts of product, which means that at equilibrium, we are going to have 0.085 minus X molar phenylacetic acid. We are going to have X molar hydronium, and we are going to have X molar phenylacetate. Now, the real key on this one is we haven't been given a Ka. So we're not solving this ICE table to figure out what X is. We're actually going to solve this ICE table to figure out what Ka is. Now, where is that other piece of information coming from? Well, it's coming from our pH. Remember that pH is equal to the negative log of the hydronium, H3O plus, concentration. So with a pH of 2.68, I can figure out the concentration of that hydronium ion by first moving that negative over. And then to get rid of the logarithm, we are going to need to take the antilog. Antilog you can find on your calculator as the secondary function of the logarithm. It's the one that has the 10, and it takes the 10 to the power of negative 2.68 in this case to figure out what the concentration of H3O plus is. And so we break out our. All right, so after all that, to go get our calculator, we put in our 2.68, make that a negative, and then 10 to the x gives us our value. And so our concentration of hydronium is 0.0021 molar. Now, the question you might be asking yourself is why only two significant figures for that concentration? Well, the rule of thumb for pH is that for every significant figure in the concentration, that is the number of decimal places in the pH that you record. So with that in mind, if we're going in the opposite direction, we had 2 decimal places in the pH. That means that we're going to have 2 significant figures in our concentration. So with that now all in place, we know that this is our concentration of hydronium, which is also equal to our X value, which means that we can now finish off the bottom line. 0.085 minus X would give us 0.085 minus 0.0021. So we get 0.0823 molar as our phenylacetic acid concentration. For our hydronium concentration, it's still the 0.0021 molar, as it is for the phenyl acetate as well. And so now with this information in front of us, we can do two things. First of all, we can solve for K. So Ka is equal to the concentration of the hydronium, 0.0021, multiplied by the concentration of the phenylacetate, 0.0021, divided by the concentration of the phenylacetic acid, 0.083. And that means our Ka value 0.0021 squared divided by 0.083 gives a Ka value in scientific notation 5.3 times 10 to the negative fifth. Now for the percent ionization, remember for percent ionization, it is the concentration of H plus at equilibrium divided by the concentration of HA initially times 100%. So we've got 0.0021 molar here divided by 0.085 molar here times 100%. 0.0021 divided by 0.085 multiplied by 100, 2.5 to correct number of significant figures, 2.5% ionized. So we can see that not a whole lot of ionization happens here. Remember in Chem 105, we said just as a general rule of thumb, weak acids dissociate about at a 5% clip, with 95% remaining undissociated. Well, that was a real approximation. In reality, it varies widely based upon what that value of Ka actually is. But to address another point that is going to come up, and this is going to come up in particular in the in-person lab, E22, we want to look at the concept of acid strength, because acid strength actually has a lot more to it than meets the eye. There are three primary factors that go into whether an acid is going to be strong or if it's going to be weak. And how strong and how weak those acids are. The first is polarity. It's relatively simple. The more polar the bond is, the stronger the acid is going to be, because the more that the electrons are being pulled away from that hydrogen, more easily that hydrogen will just pop off. Bond strength. The weaker the bond. So we've got an OH bond there. Not all OH bonds are created equal. Yes, we give you an average bond energy, but some of those bond energies are impacted by some of the other things that are going on inside the molecule. The weaker this bond is, the easier it is to break, and the stronger the acid will be. And the last factor is ionization, in terms of how stable is that conjugate base. If the conjugate base is really, really, really stable, then it's much more likely to ionize and to create that conjugate base. If the conjugate base is unstable, then it's much less likely that we're going to see deprotonation and acid formation occurring. For binary acids, we can consider the following as kind of general trends for increasing and decreasing acid strength. What we can see is that when we look within a group, that bond strength is going to matter the most. And so as we go down a group, we tend to see that acid strength increases, because we've got hydrogen, which is basically unchanged in terms of its size. But as we go down the group, the atom that is bonded to the hydrogen gets bigger and bigger and bigger. And if you remember from Chem 105, the bigger those atoms get, the greater the distance between the nuclei, the weaker the bond ends up being. And so as those groups get bigger and bigger and bigger, the strength of that bond gets lesser and lesser and lesser, and the strength of the acid goes up as a result. Within a group, or excuse me, within a period, so as we go across a row on the periodic table, we're going to rely more heavily on polarity. We know that as we go across a row, we are going to increase in our electronegativity. That increase in electronegativity is going to result in a more polar bond that is more easily broken. And as a result, the halogenated acids are stronger acids than these oxygen group-based acids. When we look at ternary acids, otherwise known as oxoacids, we need to look at polarity as well, but we're not looking at the polarity of the OH group, because that really doesn't change much. What we're going to look at is the polarity next to that oxygen. In particular, what's this element here doing? The more polar that this Y group is, the more it's going to pull electrons away from this bond, which is going to make the OH bond weaker. So take a look at the differences here. The electronegativity of chlorine versus bromine versus iodine. And we can see that as our electronegativity dips, so does our dissociation constant. And this is true kind of across the board. So here are our hypochlorous, hypobromous, hypoiodous acids. The electronegativity of those halogens has a significant role in the dissociation constant for the acid itself. The other thing to consider also is oxygens. So in these cases, if you look, here's our OH group in each case. And we can see that the atom that is bonded to the OH is chlorine in each case. But look what's happening as we add oxygens, more oxygens to that chlorine. We see that our Ka values increase and increase and increase and increase. Why do they increase? Well, oxygen is electronegative also. And so that pulling away effect that we saw becomes greater the more oxygens that we add, because the more oxygens we add, the more that we get that pulling effect, and that weakens the OH bond and makes the acid stronger because it's easier to break that bond. Now, the last point that we want to make with regard to something that we're going to see in the in-person thermodynamics lab is the idea of something called the half equivalence point. Now, you're familiar already in titrations with the equivalence point. The equivalence point is just where we even out the amount of acid and the amount of base that has been added. The half equivalence point applies when we look at weak acids and weak bases, because what we can do at the half equivalence point is a really interesting phenomenon takes place there. For a weak acid, the pH at the half equivalence point is equal to the pKa for that acid. And the pKa is just the negative log of the Ka for that acid. So at the half equivalence point, what's really cool here is you're going to do a titration, and then you're going to go and you're going to double back and basically do a half titration. So what you'll do is you're going to have 20 milliliters of acid. You're going to titrate that all the way to the end. And then you're going to add another 20 milliliters of acid on top. Well, you might think to yourself, well, that's kind of counterintuitive. Why would we go all that way? Well, the thing is, by doing that, you've titrated the first 20 milliliters of acid, but now there are 40 milliliters of acid in there. You are at the half equivalence point. And so at the half equivalence point, you can take that pH, measure it, and that is going to give you the pKa for the acid, which you can then turn into the Ka. So that's kind of the theory behind both of these experiments. Let's now go into lab archives and look at the experiments themselves and the pre-labs that you need to do. So we're going to open up lab archives here. Let's look first at the simulation. And you can see that in the simulation for the pre-lab, you're going to be doing a lot of the kinds of things that we just talked about in that little PowerPoint show. So question number 1 here, calculate the concentration of an HCl solution that has been diluted 1 to 7. All that really means is that you need to figure out what the new concentration of the HCl is, and then take that concentration, put it directly into the pH equation. And actually, for number 1, I take that back. You only need the concentration. For numbers 2 and 3, pH and pOH, very, very straightforward. pH is equal to the negative log of the H plus concentration. So that solves A, the pH for the acid. pOH is equal to 14 minus the pH. So for the acid, that's what you do. For number 3, you take the POH first. And then reverse the process. pH is equal to 14 minus the POH. And then for numbers 4 and 5, you're going to set up an ICE table. It's going to be a little bit different than one I did in the example. In this case, you're going to be solving for the hydronium concentration in number 4 to figure out the pH, and the hydroxide concentration in number 5 to figure out the POH, and then flip that around to find the pH. So that's the pre-lab for the virtual lab for this week. I will publish a separate video on Monday that's going to walk through the actual experiment yourself and kind of show you how to do the simulation. But we're going to leave that one alone for now. Let's look at E22 and its pre-lab. What you see in E22 for the pre-lab itself is you're doing the half neutralization procedure, and you get a pH reading of 3.27. So the half neutralization, again, that's the half equivalence point. So this pH of 3.27 is also equal to the pKa for this acid. So 10 to the negative 3.27 would give you the Ka for that. That's the acid constant. That's what we want for number 1. In number 2, you're going to use that Ka value and this pH value to figure out the percent ionization. When you know what the percent ionization is, the remainder, so let's say that the percent ionization was 3%, then that means that 97% was unionized. So when you figure out number 2, number 3 is the remainder from 100. For number 4 and number 5, you need to go back to the introduction section here, because we need to figure out what the enthalpy of ionization is based upon the enthalpy of neutralization. The equations for that are here in the preliminary discussion. So the pH, or excuse me, the enthalpy of ionization is equal to the neutralization plus 56.9 kilojoules per mole. So if we know the neutralization, we add 56.9 kilojoules per mole to that. And then for number 5, using our percent unionized, we divide our pH of ionization, or I keep saying pH, the enthalpy of ionization divided by that fraction to get the last value that we're looking for. So in number 5, it is the DH of ionization from number 4 divided by the unionized fraction from number 3. And if I take that ratio, that'll give me the answer for number 5. So a lot of moving pieces and parts in this, but once we kind of get into the lab itself, we can kind of work through this. This lab's actually relatively straightforward and easy to do. And we get some pretty interesting data from it that go along with what we were talking about in that second half of that kind of review that I did, where we're evaluating strength of acid based on structure. So that's all for this particular video. As I said, look out on YouTube on Monday. I will give you a more detailed kind of walkthrough of the virtual lab for this week. But until then, have a great day, and I will see you in lab.